Usually I give talks about what features C++ has and how you use them well, and try to explain why they run C++ on L2 and other strange places. This talk is a little bit different. I want to talk about roughly this. That is, what were the design principles, what were the design processes that led to that graph going up, mostly, over 4 decades. You don't do that just by language features. So this one is slow. Whoa, come on. So, according to Dennis Ritchie, there's 2 kinds of languages. Languages that are designed to prove a point, and languages that are designed to solve a problem. C and C++ are most definitely in the category of trying to solve a problem. So first I have to explain the problem. Something here. It's very slow. That's what Dennis said. And C++, I sort of started at when I wanted to build a distributed Unix system back in 1979. And if I'd ever gotten to build that system, it would have been the first Unix cluster or something like that, many years earlier. But I realized I couldn't do it. There was endless reasons why I couldn't do it. Most of them I didn't know. But the main problem I faced was that there was no language that could do what I needed to do to build this distributed Unix. There was 2 things I needed. One was something for doing low-level programming. I wanted to write process schedulers, I wanted to write memory managers, I wanted to write device drivers, things like that, network drivers, that kind of stuff. On the other hand, that with the languages at the time, like C, gave to a bunch of spaghetti that didn't quite separate. You wanted to be able to say, this piece of code, this functionality is over here, and this is over there, and they talk in this particular way. So I needed higher level facilities that I had experienced with the programming language Simula. So high level stuff for abstractions, for organizing your code, and low level things for doing bit fiddling. And well, no language at the time could do both. And to this day, languages are usually not designed to do both. So the idea was to take classes from Simula and put them into C and make them run fast enough for the kind of systems programming I wanted to do. However, I also wanted to have the idea, I liked the type system from Simula, safe and extensible, and I like optimal performance from C. My slogan at the time was not a byte, not a cycle lost. This was important. Let's see if this one works. It's slow. That led to C++ that rests on 2 foundations, a good map to hardware, starting with C, and basically going to the weird kind of hardware we have today. It has kept up with the hardware architectures over the decades. I started this work on a machine that was shared with 40 people. We could each get 250K per process, and we didn't have a megahertz. I dreamt of having a megahertz and a megabyte, and that came a few years later. So we have to handle hardware. Hardware changes constantly. Also, abstraction must be general and affordable, because if you want to get away from this and write code that is safe and elegant and productive maintenance and maintainable and such, we need to get away from that, and we have to be able to afford it. It's not good enough to be able to do it. You have to be able to afford it on a computer you can afford. Okay, so that led to interesting things. All the pictures have something to do with C++. Maybe if I point like that. No? There's a major delay here. Okay, so one thing to remember with programming, and I find that it's very often lost when we discuss the technical details, is that we write code for people and we are people. So programming language is a tool for building things that are actually useful. Our end users don't care about programming languages or even computers. I mean, a coffee machine may have a computer. I know coffee machines that do. And they are not thinking about it as a computer. Similarly, a modern car is a distributed system of maybe a couple of hundred processors. We do not say, oh, there's a distributed system coming down the road. We say there's a car. Okay, so it's a tool. And the opening statement of my first book that introduced C++ to a larger world, it's a general purpose programming language designed to make programming enjoyable for the serious programmer. By serious programmer, I mean people who write code that other people depend on. I'm very keen on dependability, on affordability, maintainability, reliability, all of these good things. I mean, think when you're building something for kids, things get really very unpleasant if it doesn't work. And design and programming are human, and part of designing a language, working with a community, is actually to make sure that you remember this and don't try and make it into something inhuman. Tick. See. Okay, good engineering relies on feedback. So it's not just math, it's not just slideware, it's not just compilers or math, it's something that has to work. And so clearly I couldn't build a language that was perfect for everybody, for everything, for all time. I have to decide what the problem was for, and it's basically for things that are complex and require access to hardware for performance. And we start with what we have. The world changes, we change, and design decisions has to be guided by real-world problems. That's the engineering part of it. Okay, so you can't actually aim for evolving a language without having some principles through which you evolve it. So I started working on some principles, and in '94, I documented it in that book there, The Design and Evolution of C++, and I set a bunch of criteria. Most of them were not language technical things, but here are some of the language technical ones, like, well, don't get involved in trying for perfection. You don't know what it's perfect for anyway. Make a transition path. And you can see here, I wanted type safety, some of them goes in. I wanted direct use of hardware for performance and flexibility. And I wanted to get away from the hardware. That is reflected again in the criteria. There's, there was maybe 25 of them in the book. These are key things, and you'll see them re-emerging in various forms. Okay. So, we have to balance concerns when we are evolving a language. And people always want roughly the same things, and quite reasonably. We want a simpler language. C++ is big and complex. We want a more powerful language, new features, ability to handle new problem domains. And we want stability because, well, we build systems that don't actually fail. And if a system succeeds, it lasts for all things. So typically I get this kind of request, so maybe at least twice a month. 1, simplify C++. We want it simpler. 2, while you're at it, I really, really need these 2 extra features. They are important. And whatever you do, don't break my code. I have 1 million lines of it, and I can't afford to rewrite it. So here we have, well, a trilemma, if there is such a word. Okay, so tick, tick, tick. So why evolve? There's a solution to this problem. You just eliminate evolution, you just rewrite everything in a new language every 5 years. This is what I think about as the multi-billion line code problem. You can't do it, you can't afford it. Some people can do it, they can use a new language, but to be honest and helpful to the users that are using C++, that I feel a little bit of responsibility for, we have to evolve. Our problems change, the world changed, so we have to evolve the language to meet the challenges, and we change. We learn new approaches, new ways of solving things, and you can't just get stuck in the 1980s or something like that. And well, there's this quote from me, I don't believe in absolute perfection for everybody and everything. We just have to do the engineering to make it really good. This gives you an idea of the scale of evolution we're talking about. And after a while, when a language succeeds, it becomes no longer something that can be done by a single individual or a small group of people. So what do? You see here the kind of things that you run into rather quickly when you get users. And C++ did not have a rich owner, did not have a sort of a sugar daddy that would throw millions of dollars into development. For a long time it was me, then it was me or a couple of friends and such. But once we are over that, we have many, many people involved. How do you organize the evolution of the language from a human point of view? I'm not talking language technical things here. Some languages have had a dictator for life. That has never been feasible in the C++ world. There's people who think everybody can contribute. So everybody are equally good at language design and thinks about the whole community all the time. No, that doesn't work either. You have to have some kind of selection and design issue, and standardization by a standard organization. This was where we ended up, not because I planned it, but because representatives from IBM, Sun, and HP, at the time the largest computer manufacturers in the world, came and started twisting my arm. You really, really want to standardize C++ under the rules of ISO. And I said, but I'm a researcher, I'm building this stuff, I'm not finished, I'm not ready, it's imperfect, it's incomplete. And they said, no, you don't understand it, Bjarne. We will trust you, but we can't trust your employer. Our organizations cannot depend on a language owned by somebody that might be our competitor. We really want formal standardization. Oh yeah, and by the way, we won't risk you getting run over by a bus. So this was I didn't have a choice. We ended up there. And it probably was the right choice. And my idea, if you ask me what I really would have liked, if I could have done it back in the ages before we got on the current path, I wanted a small secretariat with some people that changed slowly over time, so you have an organizational memory, and you have a small group that does the decision polishing, experimentation, planning, and then you have a large active community that contributes, evaluates, makes suggestions, and then your decisions filter up through layers of increased knowledge and increased care for the whole community. This is very hard. We couldn't do it because, among other things, it requires stable funding, broad knowledge, and slowly changing membership. We never got to there. So that's my ideal, and we have had to do without it. Instead, we have this. That is the C++ Standards Committee in Prague in February 2020. We just got out before the COVID. And so to get something into C++, you have to convince 95% of those people. And they are smart, energetic people with a very great varying backgrounds and interests. We don't work on simple democracy, 52 wins, 48 loses. We have a group like that, and we have to have agreement. It's about the size of this room. About 250 people turns up, and there's another 250 that takes part in the community activity in the standards. And basically, what we're aiming for is stability and vendor neutrality. That's what a formal standards committee can help you get. No guarantees, but we can do it. Usually we have been able to manage to do it. So basically, the organization under the C++ committee, you can find all the details on the ISO CPP website. That's the C++ Foundation's website. 4 working groups, 19 study groups, 4 groups looking at cross-cutting, performance, safety, things like that, and a direction group that tries to build on the work we have on criteria, ideals, direction, and such. Again, you can just look it up. And you find all the papers. You can find the head of a few top papers there, and you can find all the papers by typing in WG21 in your browser, and you get all the papers back to 1990. This is more than anybody wants to know about C++. 90+% of the members are from industry. It's very much an industrial language. We have a few academics, but the aim is to build systems in industry for industrial stuff. There's 19 nations that sent representatives to the meetings when we still had face-to-face meetings, and they all have to vote. In the end, things are voted out by the nations, and we have never had a vote on a standard that's less than 21-0. So when I say we work on a consensus, we're actually working very hard. And when people sometimes wonder, why does it take so long to get something new? The answer is, first you have to convince at least 250 technical experts, and then you have to have them sign off to their nations so they vote. On the other hand, that means that things don't break easily. Let's see. Yes, and many smaller meetings, many online meetings. There's meetings in Hawaii and people think we sit on a beach drinking strange drinks. What really happens is we have about 14 to 16 hour days, mostly in dark rooms. This is tough. You need a vacation after you come back from a standards meeting. And progress has to focus on major issues, and it's very hard to keep things on track. Okay, so there's a lot of problems to do with keeping a large language on track, like COVID. Our ambition level for C++ 23 has had to come down a bit because, well, we couldn't meet, and there are things that are not done very well over the web. There's single issue interest. There's people who says, I want this one thing and I don't care about the rest of the language. In my opinion, that has to be stopped. It has to fit into the overall language. You can take what people want and somehow get it fitted in with the rest, but you can't just have a bunch of isolated features. Sometimes we discuss, should it be in the language, should it be in the library, should it be a tool thing? And well, all of these things come in. Try to schedule a distributed meeting across the world. A lot of you know how problematic that is. And one of the things that we have to be careful about is to avoid design by committee. And really, this is designed by a federation of committees, and that also takes time, and that's one of the problems we have to guide. We have to try and avoid that, and I think on average we did. There's things that in retrospect should have been done differently, but we've been doing all right. Yeah. So let's get to some technical issues here. One of the things that I started on immediately with civil classes that was resource management. I was building a distributed system. You have to know how you handle your resources. And a resource is anything that has to be acquired and then later released. Typically, people talk about memory and memory management. I don't. Memory is a resource, file handles, logs, transactions, shaders in a graphics system, sockets, the works. It's anything that you acquire and you have to keep back. Now, every librarian will tell you that people will take books out and forget to hand them back. This is not a computer science problem. This is just the fact that we're much better at getting things than to hand it back, and it gets unreliable. So, resource release must be implicit, it must be guaranteed. If you leak something, sooner or later your system goes down or stops or whatever it does. And it has to be general, it has to handle anything that is a resource. It has to be predictable and prompt, at least in the kind of systems I'm most interested in. I know not every system I care about performance, and certainly not to the degree I do, but the C++ is designed so that it can also handle such systems. Of course, once you can handle the strictest requirements, you can handle a lot of other things, and can't afford significant runtime support. Yesterday, I listened to a talk in Cracow about a guy who was doing programming for a power controller. He had 1K of memory. For that kind of stuff, you don't want a significant runtime system. They don't tend to fit in 1K, not 1 meg. Okay, it's still key to a lot of C++. So the way you do that is you always have to lift from one level of abstraction. Here we have pointers, it's basically memory addresses and sizes. You want to lift it to something which is a vector, which you can copy and move around and change the size of and things like that. So we go from the level here, which is a representation, to the next level, and then you keep doing it. You can build things on top of this again. And basically the key notion for resources here is that you have constructors that makes this user-defined thing, and a destructor that cleans up afterwards. So resources is acquired in the constructor. It also establishes an invariant if you need one, and it's cleaned up in vector. And that means that we can do something like do we have a spare battery for this thing? I think the problem is in the battery. Oh, God. Do you have a battery for this thing? Because this is really distracting. Okay, I'll try and carry on, but see, we create a vector, we use it, and at the end of the scope, everything is released. In this case, for the vector, it's just the memory you allocated in the constructor, and the destructor do that. That's the key thing in C++. It came in the first 2 weeks of development. Okay, here's an example of a resource that's not so conventional. I have some here that's a final action. Basically, it takes an action, stores it away. And the constructor stores it away, the destructor calls it, and so I can have a function that makes one of these things, and then what I can do is use it like that. I say, finally, I want to say goodbye. And then I do whatever I want to do, and down there at the end of the scope, the destructor fires, and we get this result. This is an example of how you can do anything with constructor destructors, and it's also my answer to why C++ doesn't have a finally language construct. The answer is because we can do better through abstraction. Okay, so this idea called resource acquisition is initialization, is pervasive in the C++ standard library. All the containers use it, and a lot of things that aren't containers use it also in the way finally was done, in the way we handle file handles and things like that. So garbage collection is neither ideal nor sufficient. It takes up resources, it makes timing unpredictable, and a lot of these things are in the handle and value model of things. You provide an interface that's convenient and gives you the semantics you want, and then you implement it with something else. I hope. Oh God. Okay, so that was resources. The other thing that comes in is how do you do the type system when you want to merge low-level and high-level features? I wanted uniform treatment of user-defined and built-in types. I really don't see why I should have different scope rules, all kinds of rules between a big int and integer. Big int is a user-defined type, or complex and an int. I wanted uniform. Well, C didn't generalize, it didn't provide any abstraction mechanism that created new types. And then Simula, like in many other languages, you have overheads and different rules for user-defined types. Like in Simula, you had to access user-defined types through references. You couldn't put them on the stack and such. So they weren't affordable, and meant I couldn't afford to use user-defined types in these systems that I was planning for. Complete type safety was available in Simula, not in C. It's impossible when you can fiddle with hardware in general, but you can get very close and you can detect when you violate it. I'll get back to that. I wanted parameterized types. I wanted something like a vector. And unless you're a physicist, you want vectors of other things than just doubles. And so vector of t, where t is a type, I want to define my abstraction like that. And for that, I needed a uniform notion of types. At the time, I thought macros was a great thing for that. I soon found otherwise. And I wanted class hierarchies. I'd learned object-oriented programming from Christian Nygaard, who invented it, and was one of the inventors of Simula. And so we have that. That's, by the way, the Mars copter that was there. Its flight control is in C++. Let's see. So how do we improve performance? Because type system and performance actually are closely related. I don't believe you have to choose between high-level code and low-level code. I want high-level code that runs efficiently because it's implemented efficiently in low-level code. And basically the answer is make the language more expressive. Allow people to say what they say, they want to say, and that also provides type safety and it provides performance. If I understand what the code does, there's a good chance that the optimizer also does it. You have to express things in such a way that it's not convoluted, difficult to understand. So we also move a lot of computation from runtime to compile time. We can call const expr functions. There are functions that can be run at compile time. And it's hard to beat performance of something that's been done at compile time. And there's a lot of things here, but basically the key to performance and safety and expressiveness is a better type system. And our abstraction mechanisms for building these abstractions, of course, we start with functions, and we make them more flexible. We have lambdas and things like that. We make them possible to be used at compile time so that we don't have to fiddle around with macros and low-level code. Of course, user-defined type, the simple types like complex numbers and points. and then hierarchical organization, that's classical object-oriented programming, and generic programming, which is types and functions parameterized with other types and functions. And that's what I'm going to talk about now. I started early C++. I wrote a paper in '81 wanting to get generic programming, basically containers of T, where T is an argument. And I said that macros could do it. Macros works with you and your best friend at a very small program. It does not scale. It is quite painful. Then in '87, I started working on something better than that, and it had to be extremely general and flexible. I really wanted it to be more, to do much more than I can imagine. This was a design criteria that was explicit at the time. And then I wanted to compete with C-array for performance. I wanted to build matrices and vectors that was at least as fast as C-arrays. When I say at least, if we get to a higher level, we can eliminate temporaries and things like that. We can beat the C-arrays. If we can compute things at compile time, we can beat C-pointers and arrays. And we're doing it now. I, of course, also wanted well-specified interfaces. The C function declarations, function prototypes of my handiwork, they borrowed it from C with classes. So obviously I wanted good interfaces so that I can error messages, overloading, all kinds of good things like that. I couldn't get all three. I didn't know how to get all three at the same time. Nobody I asked knew how to do it either. So I had to pick the two first one because generality and zero overhead is what C++ gets started with. And as it is now, we now have the good interfaces here. They're called concepts, and I'll show you. So basically, the C++ style generic programming is simple, safe, flexible, and faster than most alternatives I know of. And so you have a simple example here. There's a vector of integers. It becomes vector of int. We deduce the type. Here's a vector of C-style strings initialized there. This one has 1, 2, 3, 4, 5, 6 elements. This one has 3. And we can start using them. One of the things that I've always been concerned about is that you can move from older styles of programming to newer styles of programming, so it still works. So you can use qsort for this. This is pretty ugly. You can also use the C++ standard library sort. There's the way you sort a vector very often. And here we see how I'm fitting in the C-style strings there they don't behave properly. Equality of C-style strings is not equals because that's a pointer comparison. Less than is not less than because, well, less than on unrelated pointers is undefined, and anyway, it doesn't give the right answer. So I'll just tell it how to compare C-style strings, and of course I just call the strconf from the C++ standard library. That's a lambda, which is a generated function object, and so it works. So we work on, it doesn't just have to work, it has to work with the old stuff also. Okay, so how do we do that? So in the old style of templates that you've probably, most of you will have, at least a lot of you will have seen, I say I need a type, which I call random access iterator, and then my function sort takes two of those, the beginning of things that will be sorted, at the end of the things that will be sorted. This is fine. And it's sort of a pain in the neck because you have to say the beginning and the end, and 99% of the time you just want to sort a container. What kind of container? Well, a kind of container that's sortable. So I want to say here that I want something here that's a sortable range of elements, and I want to sort it, and the implementation here is the old stuff that we've had for 20-some years. And now I can say sort a vector, assuming vector is a vector. Everything's fine because sortable range is defined, as in the C++ standard library, as a random access sequence with elements that you can compare with less than. And I can try and sort a list, and it will fail because, well, it's not a random access container. Okay, how do we then say sortable range? Basically like this. Concepts are compile time functions that works on types. So I'm saying a sortable range, an R is a sortable range if it is a random access range and it has sortable iterators. So it has to have a beginning and an end that has some properties, and the properties are plus, subscript, and plus, and things like that. That's what it says in the standard. It takes about a page of English. This is not rocket science. And by the way, these things comes out of the standard library, so you don't have to define them. This is just like perfectly ordinary programming with functions, except that they're functions that manipulate types, and they're done at compile time. And now, what if I really wanted to sort lists? Well, then I can define the version here that instead of random access requires a forward range. A forward range is one you can traverse from the beginning towards the end. That's it. So what we do is that we do this. Here is a declaration of a sortable range sort. And I'm using a new functional style syntax for this. So I basically say sorts takes a reference to a sortable range, and we'll call it S. And we can do that with just the declaration. And now I have defined my sortable forward range S. And so what I do is I copy the sequence, which is forward range, so we can only go forward, into a vector, sort it, and copy it back again. And now this is sort of ugly. What it really should be is this. I know how to do it, we just haven't gotten it standardized, and we'll see when we get it. We want a vector that's a copy of S, meaning copying the elements over, and then we copy them back again. This would be really beautiful code if this actually worked. There's still work to be done for the next standard. But anyway, here now I'm doing what I did before. I sort vector, and it says, does vec meets all the criteria of a sortable range? It does. So we try and sort list. Does it meet all the criteria? No. Does it meet all the criteria of a forward range? Yes, so we pick that. We don't have to build up class hierarchies or say what the relationship between these predicates are. Basically, if only one matches, everything's fine. If two matches, it's an ambiguity. And unless the two are subsets of the other, and then in which case we pick the strictest. That's a full set of overload or resolution rules for concepts. Okay, So, one thing that we should remember, and especially should remember when you talk about programming languages, is a language is not just a definition on a piece of paper or on a file. It's a whole infrastructure of tools, libraries, IDEs, engines, books, education things, user groups, we should remember that to evolve a language, we have to get all of this carried on. One of the things that I find very sad is when I find people being taught C++ with textbooks from the 1990s and compilers that in some cases are just as old. This is sad. Okay. That's a boasting slide. C++ is very often used for foundational things, and you don't see them. I mean, you might like JavaScript, and in which case you should remember it's a C++ program. They have different application domains, but we support a lot of things: browsers, languages, game engines. That's the flight software for the Mars helicopter. Okay, code organization. Now, the old header file and include technique is a hack. It always was a hack, but it was the best that they could do back in the early 70s. And at that time, very little was in the header files. You didn't use header files for every declaration. People copied them into their code, meaning the declarations. And it is transitive. If I have a header file and it includes another header file, which includes another header file, you have to compile a lot of stuff. And it leaks information among the headers, and you can get really subtle bugs, and it doesn't serve templates well. And also today, the average header file is bigger than the average program back in 74 or thereabouts. So this is no good. And we've known that for a long, long time. The Design and Evolution book has a chapter on macros. It starts, the CP processor must die. It just took some time. It'll still take maybe a decade or more to get further. But modules are good. This is a new thing, C++ 20. You can import modules. It is not transitive. If you import two header files, it doesn't matter which order you import them with, because they don't leak information between themselves. And so much compilation can be done once only because they're sort of isolated, and that changes the way we organize the code. This is a very hard thing to get people to do. People like the way they usually do, even if it hurts them. So tooling needs to catch up. We'll get back to that. That is a coffee machine using C++ for its graphical interface. We're still using small systems. That one, by the way, was classical object-oriented programming. So here's an example of a module. I'm defining a map printer, which is the module, and I import all kinds of good stuff to implement my module. And then I implement a function, which happens to map, write out maps, fairly standard code. And I'm saying I'm exporting this template. And I'm only exporting that template. All of this stuff here is implementation detail. If you import the map printer, you don't get all of this in to pollute your code. That's key. And I'm saying faster compile times, and of course I have to demonstrate that. So here's a little example I did. I took Hello World, which include I/O streams, and I compiled it. This is the smallest program. Then I did the same, building a module std that has all of the standard library. So over there, I'm including one little part of the standard library. Here, the whole thing, at least 10 times as much code. Notice the time. This one is 10 times faster than that one. And so that's the promise. And this is, you can't expect 10 times all the time. But I tried to take the 9 most common header files, which includes things like maps and algorithms and I/O streams and the works, and try and do that trick. Use them a little bit and see what happens. You only get a 5 times speed up. But we're talking about times here. I have seen from 0 to 100 times improvements. I have seen for real-world code 25 times improvement in compile time. This is a nice carrot to dangle to get people to change their source code control. This is an argument that the bean counters can understand. You mean I can retire half of my compile servers? That'll do nice things to my energy budget. How about the floor space? I mean, this translates into real-world improvements. Boom, 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 boom. Now, all of this is good. All of this is new to at least some of you. And so basically, we want to change. The purpose of language design is to change the way we think, and basically change the way we design and implement our software. Now, people don't like to change. Most people are very comfortable doing things the old way, the good old way that they know work, rather than experimenting with new things. New things are always complicated and slow and probably don't work. And they're invented by these guys over there that are no good anyway. You have to overcome this kind of inertia, and that's hard. It takes years, it takes decades in some cases. That's why I'm not telling you to go and use concepts and modules tomorrow. But I would like you, if you write C++, to start experimenting with them tomorrow, because it actually works. But maybe your tool chain is not complete, maybe your debuggers are not up there. It takes some time to get all of this to work. The other thing is, how on earth do you teach people to write modern C++? What's modern C++? You listen, you watch things on YouTube, and there's lots of people telling you to do terribly complicated things because they have to show how advanced things can be. And you can do very advanced things in C++. But the point is, most of us, most of the time, is not actually writing that kind of complicated code. We may be using it, but we should have the code being as simple as you can. So I and a few others started something called the C++ Core Guidelines. It even have a logo. C++ didn't have a logo for at least the first 10 years, but we're learning. So basically, we distinguish between what's legal and what's good. There's things you can do, and there's things it makes sense to do in normal code. We make that distinction, and we make a set of rules that you can find on the web, and it's backed up by static analysis tools. It must be. You can't just follow a lot of rules, and you have to remember them, you have to learn them. It doesn't work. There has to be tool support. Microsoft Visual Studio ships a pretty good core guideline checker. It would be better if it was absolutely general for all compilers, but we're not there yet. Clang Tidy has some rules, but this is sort of me and a few other people, actually with many dozens of people contributing a bet on what is modern C++. It's up to C++ 17. You will not find the modules and the concept there yet. And I wrote a book that actually was one of the origins of the core guidelines. There's an advice section. Okay. So, to sum up, the key foundations of C++ is static type checking for performance and catching errors early. If I can catch an error at compile time, I don't have to write an error handler for it and handle it at runtime. And one of the things that I dislike the most is to write error handlers, because it's one of the hardest and messiest part of writing code, because you only get here if something went wrong, and then you have to start guessing what it was. So, equal support of user-defined types, value and reference semantics. I like value types, and I often need reference semantics, pointer semantics to implement it. Systematic and general resource management, scope-based constructors and destructors, object-oriented programming, generic programming. You can do an incredible amount of stuff at compile time. And then direct use of machine and operating system resources. It is still a systems programming language. You can use it like that. So if the system uses threads and locks, C++ must and does support threads and locks. It just provides them with a better type system, so it's harder to make mistakes than what you are doing in C. I would rather like even higher level stuff, but it takes time. If you want the details from a historical point of view, there's some references. I presented 3 talks at 3 history of programming languages conferences. They come regular every 15 years. So those 3 presentations and 3 of the same language is, nobody else has done that. That's the camera on the Mars rover. Boom, boom. And so I'm back to here, and I think we still have time for some questions. Does somebody have a microphone? Okay, because I really can't hear, yeah.
Yeah, hi Bjarne, it's really great to see you in person. I would like to know, what do you think about Rust programming language, and do you think it can compete with C++?
There's a language called Rust? Why has nobody ever asked me that question before? Rust is an interesting example of trying to take some of the principles I outlined. It has a model, and some people like it. I tried and I found it a bit clumsy to write code with, and it takes time for it to stretch to meet the range of application areas that C++ goes to, and it still has to depend on C or C++ for a lot of things. It's claimed to be safe, but there's the trusted feature that you can use and people overuse. So it's an interesting language. It's also claimed to be fast, but we'll still see if it can be tuned to the degree that C++ code can be tuned. I sort of doubt it. It's a newer language, but we'll see. We'll see.
Thank you.
Oh, and by the way, also in Design and Evolution of C++, I wrote why I don't do language comparisons. They're very rarely fair. If I'm an expert in language A and I compare that with language B where I'm not an expert, the chances that it is a fair comparison is very low, and it works both ways, of course.
Is there any language design decision in C++ which, in your opinion, turned out to be a mistake?
Sorry, could you say that again?
Is there any language design decision in C++ which, in your opinion, turned out to be a mistake?
I think I got the major issues right. That is, if you describe the feature set, I think it's the right feature set. Now, in retrospect, I guess I could have done every single feature and their interaction better. But 2020 hindsight is not the same as 2020 foresight. We learn and we see what comes next, and there's a fair number of barnacles that you could do better. And the C++ core guidelines is part of my answer to that question. If you want specifics, I really wish I could have gotten rid of the two-way conversions in the C standard types, especially the signed, unsigned, implicit conversions. That's just wrong. And if you can find a time machine, go back to 86 or 87 and explain concepts to me. That would have made it much easier to implement and use templates. But you see the distinction. Templates and generic programming was important, but I didn't get it right at the first cut. It was just good enough that people are willing to suffer the problems. Now I have a better solution.
Hello, I have a question about concepts. Are concepts just more convenient? Are they supposed to replace static assert, or they have some more usage?
Oh no. Concepts are integrated into the type system. They are simply compile time functions on types. And that's very general. You can use them inside static asserts to make sure that code doesn't compile if you don't meet the expectations. There's a little bit of syntactic sugar, like using template, random access range really means call the predicate random access range on the argument. That's syntactic sugar. But you saw the overloading. You can't overload on static asserts very easily. If you know about SwinA and enable if, you will notice that I don't have to do both the positive and the negative thing, and they work together when you have several arguments and things like that. So they're much more than simple checks. But fundamentally, they're simple. It'll take some people to realize that they're actually simpler than the familiar alternatives. It's also easier to implement and they compile faster. This is my kind of ideal. Oh yeah, and they've got zero overhead. Zero overhead, faster compilations, harder to make mistakes at, simplifying my code. They come close for those things.
For many years, we have the standard of the core language. We have a standard for the standard library, I mean ISO standard. Do you think in any point in the future we can have a standard for, let's say, build system or dependency management tools?
Sorry, could you say that again? Two things.
So build systems, could they be standardized maybe, or recommended at least? And things like, I don't know, dependency management tools, so things
yes. I actually gave a keynote to CVPCon where I challenged the community to build better package management or build tools. Currently, the weakness of modules is that the build tools haven't caught up. There are either 3 or 4 build systems that fully supports modules, but some of the major ones don't yet. What I really proposed was not a standard build system, it was a standard interface to build systems. As usual, the industry resists. There are at least 10 build systems that some people think are the best build system. I mean, they think this one is the best system and not that one. And getting them to agree on anything, even an interface, is very hard. But I expect we will settle on a feature set, a bit like CMake settled on a feature set. But the process only started 2 years ago. We have existence proofs. We have several independently developed build tools. And then I would like package managers that fits with those build tools. And then I would like a repository for libraries that are represented as modules. But the C++ community is huge. It is mostly industrial. There are many independent tools, many independent compilers, many independent libraries. This makes it really hard to get people to agree to something, and it is a problem for users. As a user, which build system should I choose? If there's only been one, problem solved, but there's at least 10. What GUI library should I use? It's easy if there's only been one, but there's at least 25. And so the very richness of the ecosystem becomes a problem here. But yes, the problem is known, and I've been trying to agitate for people to address it.
Okay, the question I would ask you to I would like to ask is whether you think the current trend of releasing a new language standard every 3 years is just right time, or it should be shorter or longer longer? Because, for example, we've had constant expressions since C++11, but they couldn't be really used in a proper manner as we use them right now because of the features. We had to learn that we made some mistakes and we added them in later versions.
Okay, let me answer this in two parts. First, look here, standard. It took 5 years to get out to usable, to commercial use and such. And then it took about 8 years to get the first standard. And then it took 13 years to get the second standard. Now, the ISO standard for standards tended to be about 10 years. And we were very happy. We were faster than average. Now we are worse than average, and some of us said down, this will not work. This does not work. We will risk getting the next standard back 15 years after this, so that would be 2 years from now. We can't have that. That is just unacceptable. So we have to have a model for quicker releases of standards. And they're still international standards. Once you put it into the standard, you can't break it again. Okay, so what's the time scale? And we had discussions. People said 6 years, 5 years. And I said 3 years, thinking that people would agree on 4. But 3 was a really, in my opinion, a good thing. It's close enough so that we can tell people, yes, you have this great idea, but it won't meet this, it's not ready yet. But you'll get it in another 3 years if it's good enough. This will not make people clamor for delaying a standard till they get their feature in. And this was what caused this. People kept having features that really were so important they couldn't wait 10 years. 3 years is chosen as people can actually accept a delay like that. I think it's the shortest we could do. I mean, we don't have a paid secretariat to write the standards and do the testing and all of that. So let's see about Constexpr. Constexpr comes from a paper by me and Gabidros Reis. It's worth mentioning Gabidros Reis. He's also, together with me, the main designer of concepts. And he is, with a little bit of help from me, but mostly himself, the main designer of modules. He's currently at Microsoft, but we did a lot of this work when we were both professors in Texas. So we get Constexpr in here. Constexpr was claimed to be not only impossible to implement, but also useless. Some of the greatest opposition to a new feature that I've ever seen was against Constexpr. And it was hard to get it in, and it had to be minimal. It was really, really hard to get recursive Constexpr functions in. This is insane. A Constexpr function, by definition, does not have side effects, and it has to be independent of any other function. They are pure functions. How can you have pure functions that aren't recursive? And by the way, how can you use them usefully? I don't know. Anyway, this was the minimal we can come in. And we had a model for that we were trying to get here. Look, 11, 14. This was a major extension. This basically cleans up any messes, that extra features, things that we couldn't get in because we had a feature freeze. So the idea was a major feature, then a minor feature to finish the first one. And so Constexpr improved, Constexpr improved, Constexpr improved, as people realized that they were neither impossible nor useless. They were doing exactly what they were supposed to do, but this idea of people being reluctant to try new things hits that particular feature quite hard. But we're there. You can call it algorithms and use new and delete at compile time. After all, you just run a little emulator inside the compiler, Overdo it, you compile slowly, but if you do simple things, it actually compiles faster than trying to hack it with macros.
The second part of the question I would like to ask, was it considered to decouple releasing the language standard and the library standard? Because there are features that could be improved or fixed in the standard library, like const expr map, which need to wait for new standard of the language as well.
Exactly. There are people who claim that when you release a new feature, you should release the feature and not the library for that feature. That should go to the next release. They think that is the ideal, because that way they can test it properly and try it out properly. It is not my ideal, because when you have the feature and not the library support, it's really hard to use and it gets a bad reputation. In C++20, we got two things that I think is really important. Coroutines, got them back. I had them, it's my bread and butter for 10 years in the beginning. Now we got them back. Okay, they're more general, they're more flexible, and they're faster. But finally, I couldn't convince people they needed them. Now they believe it. And modules. There's not good library support for coroutines. There's not good library support there for modules. C++23 almost certainly will get module STD, which is my ideal module. Just give me the whole library. You can afford it. And coroutines will have an asynchronous and an asynchronous library extension. That's good. Notice, by the way, that we managed to get library support for concepts. There are libraries of concepts, so you don't have to fiddle with the low-level language facilities. You can just go and ask for a regular type, for instance, or a pointer type. One of the things that is wrong when you don't have libraries support is that it forces people to use the language features directly. And they are often tuned to be simple and fast, as opposed to generally and well abstracted. So, but it's a hard thing, because if you have to wait for the library support, and the library support doesn't come because people don't have the language support to test their libraries, then you might never get it. So it is unavoidable in a large group, think 500 people, that you don't get some give and take, and you don't get your ideal every time, and your ideal will tend to vary dependent on the actual concrete facts.
Hello, I would like to ask if is the release of C++23 by the will it be in time? Because of pandemic, it could be a struggle to have these meetings. Is this endangered, the release of it?
I'm sorry, I didn't understand that.
Is the release of C++23 endangered by the pandemic?
Okay, we have plans for C++23. There's actually an official plan which says better library support for coroutines, better library support for modules. We would like to look at at contracts, and we would like to look at pattern matching. And then we would have gotten some of those. We've got a little bit of the support here. We are not going to get pattern matching. We're not going to get contracts. My bet is that we would have gotten at least one of those two if it hadn't been for COVID, which basically stops us functioning at the way and the efficiency that we were used to. The other thing we were working on, but we would have liked for C++23, and we might have gotten it, is a general model of concurrency that handles both threads and coroutines, both push and pull. And those things, maybe we'll get them in C++ 26. 23 was always meant to be sort of a completion of 20 in the same way as 14 was a completion of 11, but COVID forced us to lower our expectations. It will ship on time though. This is the train model. The train leaves the station on time, and we're going to do it again. There was people that says after these things that we will always be late. No, we're shipping on time. We shipped 14, 17, and 20 on time. And the compilers were shipped often in the year where we voted in the standard. There are complete implementations, basically 3 complete implementations of C++ 20. We are in 22 now. Despite pandemic, we are there. Of course, any implementation can be improved, but we have the feature. I have personally experimented with all of this. By the way, don't go sort of over-enthusiastic trying to use the largest number of features as quickly as possible. Experiment to see whether it works for your kind of problem in your kind of environment, and then use the modern stuff.
So first of all, thank you for the talk, and I have a question related to compilation errors. Do you have are you aware of any plans how to fix compilation errors related to templates? Because each time I have bug in templates, I can see 5 screens of errors, which are quite cryptic.
Yes, template errors traditionally are spectacularly bad. And it comes back to what I said. I wanted 3 things, and the things I didn't get was better interfaces. With concepts, you get better error messages. Significant better error messages, you get them at the point where you make the error, not at link time. Now, the compilers haven't quite come up to the standard I wanted. As a matter of fact, they haven't caught up to my experimental implementation from 5 years ago. And that's because they are big frameworks and they have not quite. So the error messages are better. They are nowhere near as good as they can be, but they're much better than what you have now. And that was one of the major motivators of concepts. Apart from the fundamental things that you couldn't say what you wanted to say. You had to say, I want a type. Did you ever just want a type? Any old type? And then you use it, and then you see if it does what you expected? That was what templates did, what unconstrained templates did. And that was never the ideal. It was just all I could do back in late 80s. Now you can actually say what you want. I want a random access iterator, or I want a container, I want a pointer. And you get the error message right at the right spot. And eventually the compilers will generate superb error messages for them. I predict that confidently because I've already done it in an earlier version before it was approved for the standard. Okay, maybe this is a good idea to give me a break now. Thank you.